So this lecture, we're going to talk about stress. We've just spent a week or two talking about strain. These are very different things that we need to distinguish. So strain is deformation of rocks. And stress is what causes deformation. So why do rocks deform? They deform in response to stress. So stress is equal to force over area. So the basic idea is, force is important, but the area over which it's distributed is what really causes, what really matters in terms of deformation. And we're interested in studying stress in geology. There's some practical reasons as well as just trying to understand the deformation of faults and folds. Water behind a dam adds stress to the rocks and to the dam, and can cause a lot of problems if it's not carefully taken into account. And also in mining, it's very important as you're hollowing out caverns in the rock to have a very good understanding of the stresses that you're imposing on the remaining rock, or you can have some pretty serious problems. So the forces that are acting on rocks are basically gravitational and tectonic. And we can get a sense of the units and of the magnitudes of stress that rocks feel by looking at a simple case of stress in the gravitational field. So the question is, what is the force and stress acting on a 1 meter cube block at 10 kilometers depth? Due to the overlying column of rock. So we have this cube of rock of 1 meter by 1 meter by 1 meter, and it's buried under a lot of additional rock. That could be the surface. This would be 10 kilometers. So how much stress is that rock feeling? So we can address this question using this famous formula, Newton's second law. Force equals mass times acceleration. So acceleration is going to be the acceleration of gravity, or g. And we can get mass by multiplying density times volume. So typical crustal rocks have a density of about 2,700 kilograms per meter cubed. the volume of rock overlying the cube of rock that we're talking about is going to be 10 to the 4 meters cubed. So we get that from sort of 1 meter times 1 meter times 10 kilometers. 10 kilometers being 10,000 meters, 10 to the 4. So this will give us mass times gravity, 9.8 meters per second squared here on Earth. And this turns out to be about 2.7 times 10 to the 8th kilograms meter per second squared. So the meters cancel. We have kilogram meters per second squared, which is the same as newtons. That's the force. And remembering that force or stress is force per area. So the units for stress of Pascal, which is a Newton per meter squared. So this leads to the stress that this rock feels buried 10 kilometers down is 2.7 times 10 to the 8th pascals, or much easier to talk about megapascals, 270 megapascals. So just to get a sense of what a megapascal is, 1 megapascal is about 145 pounds per square inch. So you can imagine a sort of a ballerina up on her toe. It's about a 1-inch area, and she might weigh about 145 pounds. So 1 megapascal is about that much pressure. So this is the stress that this rock feels on a perfectly vertical face. So the next question then is, what about other orientations of faces? What stress is felt on a horizontal face or an inclined face? And to address that, we need more than just a single number to define the state of stress. We have something called the stress tensor. So a tensor describes the state of stress at a point. And tells you the information in all different directions. So it's a quantity that fully describes the state of stress on any plane with any orientation at a given point in time and space. So stress tensor has 9 components. So you might be wondering, what am I talking about? 9 components of stress. So one way to think about this is the difference between what we could call normal stress and shear stress. So a normal stress, let's see, let's start down here. Normal stress, which we're going to abbreviate with sigma, is a component acting perpendicular to a surface. And a shear stress tau is a component acting parallel to a surface. So we could think about this as basically, if I had a table surface here, and I could rest my hand on it, and I have some of the stress that this table surface feels is going to be the amount I'm pushing down on the surface. Another component is going to be how much stress there is that's going to cause sort of motion of my hand sliding on the table. So the downward stress is the normal stress, and that stress that wants things to slide is the shear stress. So that's just 2 components, but you can imagine, if we're talking about sort of one little point on that surface, one little point on that surface is also one little point on that surface and that surface and that surface. It's a 3-dimensional question of planes in all different orientations at that point. And this is just one of those planes. So you can imagine that you would need more than just those 2 numbers to describe the state of stress at that point. Fortunately, we can often simplify the situation to just talk about the normal and the shear stress. So for any stress state, there are 3 perpendicular planes, or 3 perpendicular planes exist where shear stress is 0. The normal stresses perpendicular to these planes are what we call the principal stresses. So the principal stresses are what we call sigma 1, which is greater than sigma 2, which is greater than sigma 3. So we can imagine that little point that is on that plane as a little tiny cube, and it's feeling on each surface of it some normal stress. We could just arbitrarily label those as sigma 1, 2, and 3 that we were just talking about. And each surface is going to feel shear stresses in both directions on that plane. And I'm not worrying about the sign conventions here. We're not going to get into it to that level of detail. But you can see, if you think of it like this, there's 9 elements here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I had said before, if these are sigma 1, 2, and 3, then in this special case, all those shear stresses would be 0. So we could define the state of stress with just 3 numbers. So if sigma 1 is in sigma 1 through sigma 3 are all equal, we call that lithostatic stress. So this would basically be similar to hydrostatic pressure. So if you jump in a swimming pool, you're feeling sort of the pressure is equal in all directions. So this tends to cause sort of compression, so a bit of volume reduction, but it's not going to do it's not going to bend or break things. What does bend or break things is what we call differential stress, which is the difference between the largest and the smallest components of stress. This is what causes deformation. Most deformation.